Hello everyone. In this video we're going to be doing some review for our second exam. I'm going to be working through various example problems, starting with some homogeneous equations. We're going to be finding the general solutions. Then we'll transition into other problems such as initial value problems, non-homogeneous equations, and also talking a little bit about application questions. All right, so let's get started here. The first thing that we want to do for any questions of this type, let's start with this example here, y double prime minus 7y prime plus 12y equals 0. We're going to be writing down the characteristic equation. And we note that the power of r is equal to the number of primes for each of our terms here. We want to see if we can factor this if possible, and if not, use the quadratic formula. Two numbers that add to be -7 and multiply to be 12 are -3 and -4. So this does factor. And what that allows us to do is write our general solution as this. C1 e to the 3t plus C2 e to the 4t, because our roots are real and distinct. Okay? That's all there is, because we have no initial conditions to apply for this problem. Moving to the next example, we again look at this and write down our homogeneous solution, or sorry, we're trying to find the solution of the homogeneous equation. So we write down our characteristic equation. Here we have r squared plus 2r plus 1 equals 0. And for this case, it also factors, but we see that we're going to have repeated roots here. Because we have repeated roots, we use our information from the section that covers reduction of order, and recall that the way that we fix this is by adding a factor of t here to the second solution to make it not linearly dependent upon the first one, and the development is contained in that section as to why this is the solution that we get in this case. But it's okay for us if we're finding homogeneous solutions to just use that answer. That's perfectly fine. Okay. Next up, what we're going to be looking at is our next example down here. We write down the characteristic equation to get this. Now again, I want to note that the number of primes tells us what the power of r is. Okay. It's a very common mistake to make. In the last two examples were chosen because they're related due to a very common error that I see that I will point out. If we factor this expression, we see that we get r and r plus 4. So our roots are going to be 0 and -4, which allows us to write down that we have C1 e to the 0 times t. So we're just going to write C1 here, and then C2 e to the -4t as our general solution. Lastly, we have y double prime plus 4y equals 0. The characteristic equation for this is r squared plus 4. And I want to point out, as I mentioned just a bit ago, that there are a ton of times where people accidentally see this problem and write this as the characteristic equation. All right? This is a very common and very costly mistake if you are to make it, because this type of differential equation is pretty common for a variation of parameters problems in particular. And if you write down the wrong characteristic equation for that variation of parameters problem, you're sunk. There's nothing you can do. You're not going to get the right answers. So please do pay very careful attention to that. And again, the way to make sure that you get it right is to match the power of r to the number of primes. Okay. Here we find the root. We're going to get plus or minus 2i as the root of our characteristic equation. And so what that means for us is that we are going to get yt and then cosine 2t plus sine 2t. Let me write the C1 here. I forgot the linear combination for a second. Okay. And so we have this as our solution here. Now, I don't have an example picked out right now for general solutions, but if we had R look something like this, we'll say 2/3 or something, I don't know. If these ended up being the roots of the characteristic equation, then of course that means that you would write this as your general solution and proceed from there in solving whatever additional parts of the problem are necessary if you happen to have initial conditions or a non-homogeneous problem. All right, so it's very straightforward. If I ask you to find general solutions for homogeneous equations, should be quick points. And of course, this is a process that we'll always have to do whenever we are working with any type of non-homogeneous equation as well, because we always need to find the homogeneous solution as the first step. All right. Next up, we have another homogeneous equation, but this time we're going to take a look at solving the initial value problem. We begin, again, by looking at our characteristic equation. We have y double prime minus 2y prime plus 5y equals 0. So that gives us r squared minus 2r plus 5 equals 0. And this doesn't appear to factor, so let us use the quadratic formula to find the roots here. So we have r equals the additive inverse of b, which is negative 2. So two negative signs here, plus or minus the square root of b squared, negative 2 quantity squared, minus 4ac, so 4 times 1 times 5, all under the radical. And that's all over 2 times 1 in the denominator. Want to simplify here, we're going to get 2 plus or minus the square root of 4 minus 20, all over 2. So we're going to get 1 as the real part, plus or minus the square root of negative 16 over 2. So we're going to get 1 plus or minus 4i, and then we divide that by, or 4i all divided by 2, so that's just going to give us 1 plus or minus 2i. Okay, so this tells us that our roots have the form 1 plus or minus 2i, and so our general solution is going to have the form e to the t, with 1 times t, and then we're going to have c1 cosine 2t plus c2 sine 2t. And now what we want to do is apply our initial conditions. Before we do that, we're going to go ahead and take the derivative of our expression, just so that's done. We differentiate the first term and leave the second one alone. That's part of the reason why I prefer this way of writing these solutions with the e to the t already factored out. And then to complete the product rule, we leave the first function alone and then multiply by the derivative of the second. So we're going to end up with negative 2c1 sine 2t. The 2 comes from the chain rule. And then plus 2c2 cosine 2t to finish all that up. All right. Now that we have our derivatives, what we can do is apply our initial conditions. It should be fairly straightforward. Evaluating sine and cosine at pi over 2 is pretty easy. So we're going to get 0. We're going to get e to the pi halves times c1 cosine of pi plus c2 sine of pi, as the 2's multiply out. Cosine of pi is -1, sine of pi is 0. All right. And so what this tells us is that 0 is equal to e to the pi halves c1 with a minus sign, because we get that -1 there. And hence c1 has to be 0. Okay. We're happy to see that, as it makes the rest of our evaluations a lot easier to do. And for our second factor, we have e to the pi halves again. This is going to be equal to 2. c1 is 0, so that first term goes away. Plus c2 sine pi. That's also going to go away because sine of pi is 0. Plus e to the pi halves. -2 times 0 times sine of pi. Plus 2 c2 cosine pi, which we know is -1. All right. And so what we end up with here, scroll down for space, is that 2 is equal to e to the pi halves and we have -2 here because of that, and then c2. Okay, so c2, we divide, we get a minus sign. It's going to be negative e to the minus pi over 2. So our solution to the initial value problem, e to the pi halves times negative e to the pi halves. Sorry. This is e to the t out here. I made a mistake. So e to the t for this term here, those match. And then c2 is negative e to the pi halves sine 2t. And if we want to get cute and simplify those exponentials, we can rewrite the answer like so. All right. Just so it's stated, I'm not going to be super picky about the difference between this kind of thing and this kind of thing in terms of simplification. If I decide to take any points off of it, it would be something like 1 point out of 20. But don't fuss over small simplification things like this. That's not a major focus. The idea, of course, is if you can get to here and not be freaked out by the fact that one of those constants ends up being 0. That happens sometimes. It depends on what's going on with the initial conditions. Okay, so here's an example of a homogeneous equation that's a little on the technical side in terms of applying the initial conditions, but one of the ways to go through and complete that process. All right. Okay, next up, we've got a couple problems that we're going to do where we look at finding solutions to non-homogeneous equations using the method of variation of parameters. For this problem, we begin, of course, by looking at the homogeneous solution. R squared minus r plus 2 is our characteristic equation, and we look to see whether or not this is going to factor, and it appears that maybe it's not going to. So we use the quadratic equation, or quadratic formula, pardon me, in order to determine the value here. So we get minus b plus or minus the square root of b squared minus 4ac here. And then all over 2a. If we look at this expression, we're going to get 1/2 plus or minus what's going on with the term here. So this is going to be the square root of -9 underneath the radical. We're going to get 1 minus, or sorry, pardon me. We're going to get 1 minus 8. And because we have 1 minus 8, it's going to be the square root of 7 underneath the radical, and that's going to be all over 2. There's going to be a minus sign on that 7, so that's going to turn into the imaginary unit I. So what that tells us is our homogeneous solution, make that H easier to read, is going to be e to the t halves times c1 cosine radical 7 over 2t plus c2 sine radical 7 over 2t. Okay, so this is our homogeneous solution. We need this as part of the general solution because the general solution to a non-homogeneous equation is going to be this plus whatever particular solution we get from our right-hand side. Okay, but we can set the homogeneous solution off to the side for now because it clearly isn't going to impact what's going on with what we guess for the right-hand side. So now we guess a particular solution. Okay. Sometimes we use capital Y of t for this. Sometimes we may use y with a lowercase c subscript. The exact notation doesn't really matter. I tend to use this, but both of them show up in the book and the notes just for clarity's sake. All right. Now, in order for our guess to be sufficiently sophisticated, we're going to need to guess a full degree 2 polynomial here. Okay, so we need t squared, t, and the constant term. And then what we do is we plug this into our differential equation and then figure out what our constants are by creating a system. So we're going to go ahead and just compute the derivatives here so they're easier to plug in. Differentiating polynomials is quite simple, so we end up with two pretty easy expressions. And now we refer back to our original equation. So we replace y double prime with 2 times a minus 2at plus b, making sure we use parentheses for y prime, and then 2 times at squared plus bt plus c to finish things off, and that equals our right-hand side. Double check, make sure we have everything copied correctly before moving on. Seems to be okay. And now what we want to do is collect terms and set things up to where we can match coefficients. Because polynomials are equal if and only if the coefficients match. And this is the general approach for the method of undetermined coefficients. We want to set up things so that we can do coefficient matching and determine the unknown parameters of the problem after building that system. So we start off by finding all of the stuff that is multiplied by t squared, which is just one bit here, 2 times a. And then next we want to find all the stuff that's multiplied by t. Looks like that's going to be negative 2a plus b, or sorry, plus 2b. Here, the first term, and here, the second. Doesn't look like there's anything else. So the quantity negative 2a plus 2b times t. And then lastly, our constant. We have 2a from here minus b from here and 2c from here. So 2a minus b plus 2c equals our right-hand side, 4t squared minus 2t plus 0, of course, in order to get everything to match up. Okay. This gives us a system of 3 equations and 3 unknowns. 2a is going to be equal to 4, using the equation for t squared. We have negative 2a plus 2b is going to be equal to negative 2, using the equation for t. And then lastly, we have 2a minus b plus 2c is equal to 0. Okay. I've written things out here using spacing, of course, in order to make things as easy to read as possible, and also set up a potential usage of the elimination method should it be required. Now, this is one of the ones where the system is so simple to solve, it's not necessary for us to go to those lengths, but you can't guarantee that this is going to be the case. You could very easily have a system that's composed of something that looks like just these parts, and you would need to use the elimination method in order to find your system. But here we basically get it for free. A is equal to 2 because we divide both sides by 2. For b, I plug in a equals 2. I'm going to get negative 4 there. I add 4 to both sides and then divide by 2 to get that b is 1. And then lastly for c, let's be a little bit more careful about the arithmetic. We end up with 2 times 2 minus 1, so that's 3. We subtract that from both sides, and so we're going to get c is equal to negative 3 halves. Okay. So, seemingly quite straightforward. All right. And a quick double check of our results that I did with the recording paused confirms that we are indeed correct here. Okay. So, we use this information to write down our particular solution, gathering what we had before. So this is going to be these two things added together. And so our general solution was e to the t, I believe. T halves, pardon me. C1 cosine square root of 7 halves t plus C2 sine square root of 7 halves t plus our particular solution, which is 2t squared plus t minus 3 halves. When you are doing undetermined coefficients, please do be mindful of tracking which coefficients you assign to which letters so that your final answers match up. If you make a mistake based on that, I will grade it as a copy error, but it's kind of more significant of a copy error, so it'll be a 2 or 3 point sort of thing as opposed to a 1 point error that I had mentioned for other sorts of simplification mistakes. All right. All right. Let's do one more example of method of undetermined coefficients, just as a general problem to get more practice. Here we have y double prime plus y prime minus 6y equals 12e to the 3t plus 12e to the minus 2t. We start by looking at our characteristic equation, writing that down, r squared plus r minus 6 equals 0. And this is one that will factor. So we get r plus 3 and r minus 2 equals 0. Okay. And so that tells us that our homogeneous solution is equal to C1 e to the minus 3t plus C2 e to the 2t, because our roots are negative 3 and 2 respectively. Now, if we compare this to our right-hand side, this problem is in your textbook basically to be anxiety-inducing. Because if it had been the case that these signs had been different, okay, for instance, if the original problem had been written so that this was a minus sign instead, which would make this negative and this positive, then we would have the case of this being positive and this being negative, and the coefficients would match. And that changes our guess for what the right-hand side would look like. In the case that I have marked up here, where everything matches and the coefficients are the same, our guess for the form of the particular solution would need to be this. All right? The reason being that the linear dependence of the right-hand side on the general solution would cause us problems. All right? And so we would need the guess for our particular solution to be linearly independent from that. Now, if we delete all these extra markings, okay, and have just the normal problem here as represented, there isn't that issue, but that is something that you need to be aware of because we are a minus sign away from needing to do that extra work here. Okay, but there's a plus here, there's a plus here. It means that this ends up being negative 3, so everything is fine. We have our general solution. The right-hand side of our problem is not linearly dependent on it, so that's okay. And it allows us to make the guess for our particular solution. Y of t is a e to the 3t plus b e to the minus 2t. We compute our derivatives, which are very easy. long as you don't make copy mistakes. Forgetting negative signs. Okay. So we just use the chain rule for our first and second derivatives here. In order to get everything set up. Okay. So now what we can do is move to plugging all of this into our original equation. We have 9a e to the 3t plus 4b e to the minus 2t plus 3a e to the 3t minus 2b e to the minus 2t, and then minus 6 times a e to the 3t plus b e to negative 2t. Fixed my handwriting there. And then slide this over just a little bit so that we have room to put our right-hand side, which is 12e to the 3t plus 12e to the minus 2t. Okay, so a little bit cramped here. We'll make these a different color so they stand out. Now what we want to do is collect terms in order to make things as easy to read as possible. Okay. And that won't be hard to do because we have 9 factors of a here, and 3 factors of a here, and negative 6 factors of a here. So 9 plus 3 minus 6 is 6. All right. And then we're going to do for this for b now, we have 4 copies of b here, minus 2, and then minus 6. And so that ends up giving us a total of negative 4. System of 2 equations and 2 unknowns, but they're very, very simple. So we're going to end up with a being 2 and b being negative 3. Okay, and so our general solution here easy to find due to our very near miss on that issue that I talked about at the beginning of the problem. Is c1 e to the minus 3t plus c2 e to the 2t plus 2 e to the 3t minus 3 e to the negative 2t. All right, so this could have been a problem that was a little bit more work. The only difficulty in the extra work would have been our derivatives would have been more difficult to compute because we would have needed to do the product rule. But it doesn't materially change anything about how difficult the problem is other than a little bit harder of a derivative and needing to remember that we always look at whether or not there is any dependence of the right-hand side on whatever the homogeneous solution is. That's why you always have to find the homogeneous solution. You need to make sure that the powers don't match if we're talking about exponentials is the big one. There can be other problems like the arguments of sine and cosine matching. If you have cosine of 3t and there's a 3 there and a 3 in your homogeneous solution, that's a problem. But we aren't going to give you that kind of problem on the exam because we haven't discussed the implications of that. How one would adjust the right-hand side in order to make that work. So exponentials are when you need to be on your guard. So pay attention to that. All right. Let's practice one application problem of the sort that might show up on the exam. Um, there may be a circuit problem, or there may be a problem like this with a mass spring system. Okay. What I expect you to do is be able to convert the problem into a solvable ODE and then work from there. For the problems that I give you on an exam, I will make sure that the numbers are reasonable. This is a textbook problem, so if the numbers don't work out to be exactly super nice, we'll deal with it here as part of the review, but do know that I will give you reasonable arithmetic on the exam. I'm not going to try to trick anybody with nonsense numbers or anything like that, especially because in these problems the numbers can be kind of big. Okay, so we're told that the mass here is 100 grams. We can convert that, should we choose, to kilograms. Okay, so that we can use our familiar gravity constants and things like that. So we have this mass here, and then we are told that the stretch of the spring is equal to 5 centimeters. We can convert that to meters. Again, to make sure that we compute our spring constant correctly for the purposes of putting it into our equation. And we also have a velocity, which gives us an initial condition for the problem. The position, since we're told that it's equilibrium, is going to be 0 there, and the velocity at time 0 is going to be 10 centimeters per second. We can rewrite that in terms of meters per second if we so choose. Okay, I'm going to go ahead and convert everything to MKS just to do the more familiar version of things instead of giving you dynes to work with. Now, I may, on the exam, give you a problem that has dynes. If I do, I will tell you not to worry about converting the units, and we'll remind you of things like the gravity constant so that you don't have to freak out about remembering that or having it in your notes or anything like that. So, okay. So let's continue here. All right. Now we know that mass times gravity needs to be equal to the spring constant times the displacement. Okay, sum of the forces is 0. So we're going to have our 0.1 kilogram mass, 9.8 meters per second squared as gravity, and that's going to be equal to K times 0.05 here. So this is going to be K. We can do long multiplication here, get rid of the fact that they're both being divided by 100 and set things up, and get 19.6 here. So not the worst thing to have to come up with. Okay. So this is our value for K. And what that allows us to do is it allows us to write out our differential equation. Okay, this is a homogeneous equation. There's no forcing function being applied to what's going on with the spring. And so we have no U prime term because we are told that there is no damping. Okay, so gamma is 0. And it is perfectly legal to multiply by 10 to get rid of that inconvenient looking decimal there. So now we have this. Our characteristic equation is very easy to write down. Again, the number of primes tells you what the power on R is. Okay, I hope you all can tell that I see this every time I give an exam over this stuff, and I don't want you to make that mistake. All right. So R is equal to the square root of 196, which is 14. So nice round number. even though things didn't look like they were going to go that way. All right, so plus or minus, it's going to be imaginary. So we're going to have oscillatory motion here. What this allows us to do now is to write out our general solution. U of t is equal to C1 cosine 14t plus C2 sine 14t. And in order to finish the problem up here, we want to apply our initial conditions. We can go ahead and figure out what u of 0 is. We know that it's a 0. We're going to get cosine of 0 plus sine of 0 here. Sine of 0 is, of course, the 0. And so this tells us that C1 is actually equal to 0 as well, because we're going to get 0 equals C1 times 1. The next thing that we need to do is compute u prime so that we can apply that initial condition. Normally, we would go ahead and just take the derivative first, but since it was so easy to figure out the first initial condition, we did things slightly out of order. Oops. The derivative of cosine is negative sine, so we do that and apply the chain rule. And then compute this factor here to get this. Now we apply our initial condition. It's supposed to be 0.1 because of the unit conversion that we did that is slightly off screen at the moment. Okay, and we plug in 0. Sine of 0 is 0. I'm going to go ahead and skip writing that down because we don't need to worry about it. And we're going to have cosine of 0, which is 1, so we end up with this. And so what this tells us about C2 is that it is going to be equal to 0.1 divided by 14, which we can rewrite into a much nicer fraction. And we won't need to worry about decimal approximations on the exam, but if we were to compute it, kind of a small number. And so on. All right. So there we go for this one here. The final answer has the form 1 over 140 here, sine of 14t. All right. Let's do an example here where we're going to be solving a problem involving variation of parameters. Sorry, that needs to be open, not closed. Okay. Just as a note, the domain restrictions that tend to show up on these kinds of problems are mostly to make sure that there isn't any weirdness going on with the integrals that come up in these problems. So they'll say that t is positive when that's appropriate, or here we want to trap the argument of the secant here in between these values because we don't want to go outside of the range of values where secant is defined, and also because it simplifies our thoughts when we're working with trigonometric integrals, which are a pretty common occurrence in these types of problems. Okay. So, before we get started, one of the things that I want to note about the method that we're going to be using for these problems is that if you look at the notes, everything in the theory that we have for solving non-homogeneous equations with variation of parameters starts off with this expression here where the coefficient on y double prime is 1. Okay? So it is a necessary step for us at the beginning of this problem to go ahead and put things into standard form. Okay? Now, the putting it into standard form isn't going to change what we get in terms of the homogeneous solution of the problem. The roots of this are the same as the roots to this if we look at their characteristic equations. That doesn't change. But what will change are the constants that result for our particular solution. And this actually matters. Okay? So if you forget to do this, this will be like a 1 or 2 point simplification error type thing, because it does impact the final result. You will get a different answer for the particular solution if you skip this step. So please keep that in mind. All right. So if we use our characteristic equation, find its roots, and we get r equals plus or minus 1/2 I, this tells us that the homogeneous solution for this problem is going to be C1 cosine t halves plus C2 sine t halves, which we're happy to see because those arguments match up. That's what we'd expect to happen. It's going to allow us to be able to actually compute these integrals. Okay, now that I have the homogeneous solution and I have my right-hand side that I know I can't deal with using method of undetermined coefficients, we're going to use the technique of variation of parameters, which says construct the matrix equation using y1 and y2 and y1 prime and y2 prime and u and v prime. We'll use u and v this time. If you want to write u1 and u2, that's okay too. 0 and then g of t. Okay, so that's the general form. You are allowed to have this in your notes as a reminder of what in the world to do here. Okay, for our particular problem, we write in our different expressions. So we have sine and cosine and sine of t halves, and then we have the derivatives of these expressions. So negative 1/2 sine t halves. Too many dots on my I there. And then 1/2 cosine t halves times the vector u prime v prime. If you're going to use u and v, make sure that I can read and tell the difference between your u's and v's, please. And then 0 and 1/2 secant squared t halves. Okay. Now we are going to use Cramer's rule in order to set up equations for u prime and v prime. I will begin by computing the Wronskian of this original matrix, because I know that that's going to be in the denominator when we do our other computations, just to get it out of the way, so I don't have to recopy that. So this product minus this product. So I'm going to get 1/2 cosine squared plus 1/2 sine squared, which since is just 1/2 because cosine squared plus sine squared is 1, and I can factor out the 1/2s. Okay. So now u prime is going to be equal to the determinant of the matrix 0, 1/2, secant squared t halves sine t halves 1/2 cosine t halves all over 1/2. So we're going to get negative 1/2 secant squared t halves times sine t halves over 1/2. Those 1/2s are going to divide out, which is why it's important to do that initial step, because this constant would be different if we hadn't put the equation into standard form at the very beginning. Okay. And so this is secant squared times sine. I know that secant squared is actually 1 over cosine squared. And so what I can do is I can think about this entire expression as being sine over cosine times cosine in the denominator. This is tangent, and this is secant. And so this whole thing simplifies to secant times tangent, which is a very easy function to integrate. Okay, so using your trigonometric identities can be very important here. All right, next up, we do our work to find the value of v prime. We play a similar game that we had before. Now we have cosine of 1/2, negative 1/2 sine t halves, and then we substitute in the right hand side 0 and 1/2 secant squared, like so. And this whole thing gets divided by 1/2 because of the Wronskian from the original matrix. Okay, this is 1/2 cosine t secant squared, or sorry, cosine t halves times secant squared t halves all over 1/2. The 1/2s divide out, and we know that cosine and secant are reciprocals, so all that's left is just secant of t halves. And so you would need to write down the integral of secant, which is a formula that we should know from Calculus 2. If you have trouble remembering that, put it in your note sheet. All right. We can integrate now. U is the integral of secant tangent. We need to do a U substitution, but after the U substitution, we just get secant of 2t, because secant times tangent is the derivative of secant. For v, we integrate secant. End up with a factor of 2. But this should be another antiderivative formula that you know from your studies in Calculus 2. Right. And then what is left for us is to follow the final step for our solution, which is to use the assumption that I didn't write down for this example, but I hope we all are familiar with, is that we made the assumption that our solution has this form, and now we want to plug in u and v and y1 and y2 in order to get everything to work out. Okay, we're a little short on space, but U1 is 2 secant t halves plus C1, and this is going to be times cosine t halves, plus, now we have 2, the natural log, the absolute value of the secant t halves, tangent t halves. I would need to double check. I don't think the absolute values are necessary because of the domain restriction we talked about at the beginning of the problem, but I'm going to leave it there for safety's sake so that we don't accidentally write down something that's nonsense. All right, so now we have sine t halves, and what we want to do is reorganize our solution collecting terms for our expression. Okay, a couple of things. Number one, we have C1 cosine t halves plus C2 sine t halves. It should always happen when you do this method that you recover the general solution of the homogeneous equation. Always should happen. Okay? The other thing that may or may not happen is weird simplification stuff. In this problem, part of the reason why problems similar to it are pretty popular is that this happens. These two things get multiplied together, and it turns out that we're going to get just a 2 here because secant times cosine is 1. Okay? And then we're also going to get this expression with the natural logarithm. And make sure that you write this in a way to where it's clear which thing is in the logarithm and which isn't. Because if you put that sign at the end, it looks kind of strange and can be a little bit challenging. Okay. And then so again, the 2 comes from multiplying these things together. Okay, so something like this. I'm pretty sure that this was similar to a question that showed up on the quiz. But I wanted to go through it just to show the process and the benefit of paying attention to what's going on with our trigonometric functions for resolving those. All right. And then variation of parameters methods come in many forms. The best way to get ready for them is to practice because I can't tell you beforehand exactly what kind of derivative you're going to have to do, but it is very likely to involve some trigonometric functions. I'm not going to put something on there to confuse anybody, but I do have to assume that you have kind of a robust ability to do at least medium difficulty Calc 2 problems, and this falls under that. Would be dealing with a not super complicated, but a reasonably interesting trigonometric integral. All right, so please email me if you have any questions, or visit my office hours, and we'll make sure that we're ready for our exam coming up here in a couple days. All right, thanks.